Hello, Physics 30s. I want to just talk about basically the wave-particle duality theory with the two examples in theory that you need to know. One is the what's called de Broglie wavelengths, and the other one is called Heisenberg's uncertainty principle. There's a number of excellent videos that I've posted there. I encourage you to look at them. They're only about 5 or 6 minutes each. And they do a great job of explaining some of the principles and even pushing into the last unit, things like Ernest Rutherford, men like Ernest Rutherford that made contributions, J.J. Thomson, and a couple others. But anyway, so let's just dive into this. One of the things you need to know about ever since Arthur Compton's Compton effect, not too long after that, there was a Frenchman named Louis de Broglie, who was basically a lifetime student, and he made a really interesting conclusion just based on theory alone. There's a picture of him here, Louis de Broglie, and he was wondering, well, if waves can act like particles, then why can't particles act like waves? And he had a great argument for it that caught the attention of Albert Einstein. And it's actually really simple using the formulas that you have on your formula sheet. What he basically said is, yeah, the formula for momentum of an object with mass is mass times velocity. And Compton's experiments confirmed that photons have momentum. And one of their formulas is h over wavelength. So the formula for the momentum of a photon. Well, de Broglie's like, these are both the formulas for momentum, so why can't we combine them? And he's like, look, see, they just go together like this. Like we just say mv is equal to h over wavelength, and then you could manipulate the expression to solve for wavelength. And this became known as de Broglie wavelengths, okay? So you'll see that referred to in some of the review questions. And the math is pretty straightforward. The h is always Planck's constant, 6.63 times 10 to the negative 34. The mass is the mass of the object, okay, whatever it is. And the velocity is the speed of the object, or, speed with direction. Okay, so obviously if an object isn't moving, then you can't observe its wavelength. But that's really weird. That's like, as we're going to look in a minute, this means like if you throw a baseball, it has a wavelength. Like, really? What is it? So just for fun, this is already done for you, so you can just follow this pretty easy. The short of it, though, is day-to-day objects have wavelengths that are so tiny that they're imperceptible, like we could never see them. And just to show you that, let's use the de Broglie wavelength. And right here where it says determine the de Broglie wavelength of basically a baseball that's moving at 15 meters per second. Okay, 15 meters per second, that's like 50 miles an hour, or 50 kilometers per hour, sorry. That's just like throwing a baseball at someone. That's not even a fast pitch, or not even close, okay? So not a very fast speed, but it's moving. So the wavelength, as you can see here, we would plug in those numbers, kilograms, meters per second, and you get 2.21 times 10 to the negative 34. Now, that's small. As it mentions here in these notes, an atom, basically an atom, okay, the diameter of, say, a hydrogen atom, or most atoms, is that diameter is basically times 10 to the negative 15 meters. Okay, this is to the negative 34. Like, there's nothing that small. We can't make anything that small. So the de Broglie wavelength for a baseball is just, sure, according to de Broglie, we can calculate it, but there's no way we could ever measure that. But there's some scientists looked at de Broglie's formula, and they're like, look at this. If we could find something super small, like make that mass really tiny, okay, the velocity will be what it'll be. But if we can make the mass really small, then maybe we can make, sorry, let me reverse that. Then we can make the wavelength bigger. Okay, if we can make the mass really small, then maybe the wavelength will be big enough that we could observe it somehow. Okay, So what's the smallest bit of matter that we know? Well, guess what? It's an electron. And at this point, they'd understood electrons quite well. We're going to get to the electrons in the next unit. But so the theory is, and this is what they started thinking, is, oh, and that's the other thing. If you want to observe wave patterns, you're going to need to be able to kind of shoot these particles through like a double slit so that you can observe, constructive and destructive interference. And those slits need to be close to the same diameter as the wave that you're shooting through the slits, which is why, when we use diffraction gratings, when we're shining light, those gratings are really, really small. They have to be because the wavelengths are small. So anyway, this example here says, well, let's we can determine the wavelength of an electron that's accelerated through 100-volt potential difference. So what that means is, and this is really common on other tests, what we do here is we make two plates, one negative and one positive, and you introduce the electrons into this region, and then you put a voltage across, right? So from here to there, it's saying there's 100 volts, okay, of potential difference across that. So that makes this end really, really negative and makes this end really, really positive. So all that's going to happen is you do that and you're going to accelerate this electron. It's going to go from rest flying over this way. Yeah, some of them will crash into the plates, but we obviously make that little hole so that some can get out. And then, yeah, we have a vacuum chamber back here, and those electrons we can do stuff with them. We can, have a magnetic field waiting for them or an electric field waiting for them. We can bend them and have them hit stuff and do all kinds of things. Now, but using energy, this we can do basically this expression here. We can say that Q times V, right? Energy is equal to Q times V. We know the charge on an electron, multiply that by the voltage, and then we can equate that to 1/2 mv squared, because that basically electrical potential energy right here is going to become kinetic energy when it gets to the other side, okay? And so, yeah, we solve for V, we get a nice velocity here. It's not the speed of light. We come close to that, but it's ripping, okay? So now we got that velocity. We know the mass of an electron. We do the same calculation for the de Broglie wavelength, and we get a number like this, okay? Now that's a little better, 10 to the negative 10. Interestingly enough, that is really close to the size of X-rays. X-rays are times 10 to the negative 10 in their wavelengths. So, and that's a number we can play with, because actually certain crystals have their crystal lattice is close to this distance apart inside, transparent crystals. So these are the two men, Davison and Germer, and you'll see their kind of the result of their experiment in some of the videos. But they shot electrons at a crystal, and or a crystal sample, I guess, of nickel, and they observed a diffraction pattern. So that's what this picture shows right here. You cannot get this pattern if you're shooting particles at a double slit. You can only get this if there are waves passing through the double slit, because you get constructive and destructive interference patterns. So the conclusion was basically inescapable, that electrons can act like waves even though they're particles, and that's just okay. That just gets nuts. But they verified they verified de Broglie's wavelength, and so this is what we call, and this is what we should end on. This is what wave-particle duality is. Okay, you've seen me mention that before. It's called wave-particle duality. It's the theoretical principle that particles can act like waves and they can act like particles. And waves, of course, can act like particles, and waves can act like waves. So that's just cool. So anyway, what that leads us to is this last part. Now, I had to add this because it wasn't in the notes before. A German physicist named Werner Heisenberg in 1927 he came up with a principle known as Heisenberg's uncertainty principle. It's based on some pretty complex math. You don't need to know the formula for it. You just need to know the principle of it. And what he concluded was, and I've defined it for you already, he says it's impossible to know both an object's momentum or velocity and its position at the same time with unlimited precision. Okay? What he was basically studying were electrons. Okay? And so if you can imagine, maybe I'll just put this down here a little bit, because I'm going to show you some other stuff. But if you can imagine, you have a proton here, and then you have an electron, and it's orbiting the nucleus. How do you know where it is? Like, if you wanted to know where the electron was at any given moment in time, how would you know? Well, the only way you could really know is if, you might have to send in, some kind of electromagnetic wave to hit the electron and then bounce back off to a detector. So then you could say, yeah, well, I detected something at that position. But the problem was, Heisenberg realized that he couldn't know both the position and the velocity at the same time. Because if you know one of them really well, you know the other one less well. And there's also a huge challenge here, because if you start imparting energy to the electron in the very attempt of measuring it, you can knock it out of orbit. Like you can impart energy to the electron. So it was a very perplexing question, because no one really knew exactly where the electrons were. And if you really try and start drilling down where they are, if they can act as both a particle and a wave, that's actually part of the reason why they're hard to nail down. You can't really say the electron's right there, and it's right there. So famously, Albert Einstein wrestled with this conclusion, and he made this statement. He says, "God does not play dice with the universe." I love that. The theory behind that. But the point is that Einstein, and really the scientific community in general, took great pride in knowing things with certainty, that you can know with certainty with calculations, aspects and elements of the universe. But when you get down to this subatomic level, because of this wave-particle duality principle, you cannot know both the position and the momentum or velocity of an object with unlimited precision at the same time. You can't. So I've heard it explained this way, and I like this example. Imagine two photos of a Formula One racing car passing by. Okay, and I'm sketching this, so it's really ugly, but we'll do our best. You could, if you had a really fast shutter speed on a camera, and you could take, and it would get an exposure very nice and crisp, you might be able to get a picture of a race car, okay, where it's passing you going really, really fast, but your camera is so good that it could take a picture of the car and it would look like the car was parked. Okay, in my mind, I could imagine that I could read the letters on the tire, and they would be perfect. They wouldn't be blurry or anything. The letters on the tire would be clear to read. It would look like the car was parked. Okay, so if you could imagine taking a picture like that. Okay, and then in the second one, imagine taking a picture where you leave the shutter open for half of a second or even a whole second. Okay, let's say it's a whole second. So if you do that, now what happens is you would get a picture that would look something like this, where everything would be blurred over a little bit. So you'd have, the car, like the spike of the car would look like this, but then it would also be like this and like this and like this. Okay, whoops, maybe not that last one. And kind of how the cartoonists draw cartoon characters when they're moving. They have multiple, defined positions. So in the second picture, you maybe, if you knew how, if you could measure the distance, okay. So let's say, you can measure the distance from, say, here to here, okay? So you have where the image begins and where it ends, and then there's the blur in between. And if you can get a distance there, and if you knew that the time was 1 second, like if your shutter speed was open for 1 second, you could probably, and I'm just kind of being hypothetical here, you could probably figure out the velocity. Like, how fast was this car moving? Because I had my shutter speed open. My shutter was open for for 1 second, we'll say. And the smear, like the image is smeared out over a certain distance. And so I can get a sense of the velocity. But the problem is, how do you know where was the object when you took the picture? Was it, was it right here? Was it right here? Or was it right there? Like, where was it? And there's this area of uncertainty. Okay. Anyway, I'm kind of having fun with this example. So the point is, if this helps you, this is Heisenberg's uncertainty principle. You cannot know, if you want to really know the position of say a subatomic particle like an electron, you can find it, but here you would have no idea how fast it was moving. Like, this is a Formula One racing car. It's, going a couple hundred kilometers an hour. But in this picture, yeah, you know exactly where it was at that moment, but you have no idea of how fast it was moving. And then, of course, the flip side is under velocity. If we try to measure the velocity, we give up our certain knowledge of where it actually is. Now it's this smeared out, uh, uncertainty. We just don't know. So that's a very simple way of trying to explain something intensely complex as Heisenberg's uncertainty principle. But I just want you to leave this section knowing that, knowing and understanding the wave-particle duality of matter. Okay. So particles can act like waves and they can act like particles. We've seen that, or we see that in the Davison and Germer kind of electron scattering experiment, which is highlighted in some of the videos. It's kind of mind-blowing, but it's really cool. And then the other one, of course, is that waves, light can act like waves, which is obvious, but it can also act like a particle. And the two experiments that created overwhelming evidence that light is a particle are the photoelectric effect and the Compton effect. Those are the two kind of flagship experiments that confirm that light is a particle. It's a photon. Okay. So it's very fascinating moving forward into these different realms, but I will shortly get some other review stuff up.